Hey Calculus class! Today we are going to learn topic 67, Taylor and Maclaurin polynomials. So before we talk about these types of polynomials, let's do a quick review of linear approximation. So recall that the linear approximation or tangent line approximation of f at a is given by L of x is equal to f of a plus f prime of a times x minus a. And if you can recall from when we did linear approximation months ago, right, we find the y value at this specific point and say that it is the approximated y value on the curve at the same x value. So we're using the y value on the tangent line as the approximated y value on the curve. And remember that the reason we do tangent line approximation is for estimating the value of a function at a point when it is a complicated function. So let's look at a simple example. So what is the approximate value of y equals sine x at x equals pi over 2? So if we were to use linear approximation, we would set up the equation of the tangent line at pi over 2 to get the following. And then after evaluating sine pi over 2, which is 1, and cosine pi over 2, which is 0, we get that the value of sine x at pi over 2 is 1, which we pretty much knew already. And that means, that also means that your equation of your tangent line is y equals 1. So graphically, here's what we are looking at. Here's the sine curve. Here's the tangent line at y equals 1. And as we move further away from the tangent point, the error in approximation becomes greater. So remember that if we keep using the tangent line to approximate the y value at the curve at that specific x value, each time I keep moving away, that error gets bigger. So the question is, can we find a better way to approximate the value of the function? And yes, we can. And what we actually will use is a polynomial with a higher degree than 1. In linear approximation, we're only using a first degree polynomial. And if we notice that we can sketch a parabola that goes through the given point, so here is our parabola that goes through the point pi over 2, when x is pi over 2, and that it gets closer to the original curve. And as you notice, if I was to move away from that point, the error is actually smaller than it would be with y equals 1. So how do we develop a quadratic equation? So in order to approximate a function with a quadratic function, you must have three things happen. The first is that the original function and the quadratic must both go through the given point. Second, the original function and the quadratic must both have the same first derivatives. This tells us that they have the same slope. And third, the original function and the quadratic must both have the same second derivatives. This tells us that they have the same curvature or concavity. So, for us to write the quadratic approximation, we first need to rethink how we write the linear approximation. So here's our linear approximation at some x value c. And basically this is saying that we have 0 degree plus the first degree of a polynomial. So note that the 0 derivative is just the original function because we haven't taken a derivative. So this right here is just this piece. In the linear approximation, we only have the original function and the linear function go through the same point, the 0 derivative, and that the first derivatives are the same. How would we change the linear approximation so that we have a quadratic where the second derivatives are the same as well? Well, we just add another term where we have taken the second derivative. So that means that the y value is going to be approximately the original term plus with the first derivative plus with the second derivative. However, we do need to divide by 2 so that when we do take the second derivative, both derivatives are the same. So back to our simple example. So we have what's the approximation of y equals sine x at x equals pi over 2. So if I was to approximate a quadratic function around x equals pi over 2, I'm going to use this process. So I need the first derivative of my function, which is cosine, and I need my second derivative, which is negative sine x. Now when I substitute in this information into the following, I get this nice lovely polynomial where I have my value of the original at pi over 2 times the factor with the 0 power plus my derivative at pi over 2 times the factor with the first power plus the derivative, the second derivative, which was negative, hence why that's negative, times the factor squared. And I can simplify this. So I know that the cosine of pi over 2 is 0, so that's why this term cancels. This is just 1, and sine pi over 2 is also 1. And then I have sine pi over 2, which is 1 over 2, times the x minus pi over 2 squared. So I get this following quadratic to approximate the sine x. So if we look at the graph of y equals sine x, with both the linear and quadratic approximations, what do you notice? Well, you should have noticed that the quadratic approximation works better because the error is smaller over a larger range. So can we find an even better way to approximate the value of the function? Yes, use a polynomial with a higher degree. So what will you need to add to the quadratic to make it cubic? Quartic. How about a polynomial with nth degree? Well, currently here's our quadratic. If I wanted to make it cubic, I would add the third derivative term. And then of course I would have to divide, but I'm dividing by 3 factorial so that it's canceling out this 2 and this 1. And then I would add the fourth derivative, but I would need to divide by 4 factorial to cancel out these 3, 2, and 1. And so on until I get to the nth degree, and I'm dividing by n factorial. So graphically, we can see that the higher polynomial is becoming closer and closer to the original function. So as you can see, this purple graph right here is actually the quartic, and you can see how over a larger range, this quartic curve is closer to the sine curve than the quadratic curve or the linear curve. The use of polynomial approximation is an elegant and efficient way to evaluate complicated functions. And of course, when you don't have a calculator. So this leads us into Taylor polynomials. So suppose that f of x has k derivatives at the point x equals c. Then the Taylor polynomial of degree k for f of x centered at c is defined as the following. So it's basically the polynomial that I just had on the previous slide with the nth degree, but now we're saying k degree. And that means we can rewrite this as a series where the Taylor polynomial is equal to the sum of the nth degree term, where n equals 0 to k. And all derivatives up to the kth derivative of the original function and the derivatives of the Taylor polynomial approximation must be the same. So let's look at some examples. We want to find the fourth degree Taylor polynomial of y equals ln x at x equals 1. So I am taking y equals ln x, and since I want fourth degree, that means I'm going to need go all the way to the fourth derivative. So I find the first derivative, the second derivative, the third derivative, and the fourth derivative. Now I have to evaluate each function at x equals 1. So when I do that, I get 0, 1, -1, 2, and -6. Now, here is my series, or my sum, of a Taylor polynomial, and I want to go only to the fourth term, is how you can think about it. So to start out, my first term of the Taylor polynomial is going to be when n equals 0. So that just is going to leave me with the term at ln x, which was 0, plus the next term, which is going to be the first derivative 1. So since the first derivative is 1, I have 1 times x minus 1, plus the second derivative times the factor squared, plus the third derivative, and notice I'm doing over the factorials, that goes with my Taylor polynomial, times x minus 1 cubed, and then plus the fourth derivative times the factor x minus 1 to the fourth. And I can even simplify this even more. And so if here with the factorials, so we know that 3 factorial is 3 times 2 times 1, which means that the 2 and the 1 on the denominator cancels with this 2 on top. As well with the 4 factorial, which is 4 times 3 times 2 times 1, will cancel out with, if I was to expand out the 6, which is 3 times 2 times 1, it will cancel that out. So therefore, I'm left with the following Taylor polynomial. Now let's find the fourth degree Taylor polynomial of y equals cosine x at x equals 2 pi over 3. Why don't you go ahead and pause the video and see if you can do it on your own first. All right, let's see how we did. So since you want fourth degree, you need to go all the way to the fourth derivative. So our first, basically the 0 derivative, is the original function. So y equals cosine x, first derivative, second derivative, third derivative, and fourth derivative. Now I'm going to evaluate each derivative at x equals 2 pi over 3. So when I do that, I get -1/2, negative square root 3 over 2, 1/2, square root 3 over 2, -1/2. So when you write your fourth degree Taylor polynomial, you're going to have your first term, which is at the 0 derivative, and then your next term, and so on. And of course, each one's going to be multiplied by so many factors of x minus 2 pi over 3. So when you write your Taylor polynomial, you'll get the following, and after simplifying the factorials, which is what I did here, I have my final answer. All right, now let's look at what are called Maclaurin polynomials. A Maclaurin polynomial is a Taylor polynomial centered at 0. So basically, that just means that when you evaluate each of your derivatives, you're evaluating them at x equals 0 every single time. And we can write a Maclaurin polynomial as a series. And whenever you are asked to find a Maclaurin polynomial, you automatically should know that it is centered at 0. So let's look at some examples. If you want to find the fourth degree Maclaurin polynomial of y equals e to the x, notice how I didn't give you at x equals whatever, because when you see the word Maclaurin, you automatically know that x will equal 0. So since I want fourth degree, I'm going to need the fourth derivative, which for e to the x is just e to the x each time. I'm going to evaluate at x equals 0, which in this case is all 1. So when I write the Maclaurin polynomial, I will get my first term times the factor x to the 0 power, which is just 1, and I would keep going. And you can either leave it as such, or if you wanted to, you can simplify out the factorials. All right, why don't you try this one on your own? Find the third degree Maclaurin polynomial of y equals natural log of 1 plus 2x. Let's see how we did. So you're going to want to find the third derivative, and you're going to have to use the chain rule. So here's your first derivative, second derivative, third derivative, and go ahead and evaluate when x equals 0. You should get 0, 2, -4, and 16. So when you write out your third degree Maclaurin polynomial, you're just going to get the first term is just going to be times 0, so that's why I don't have anything here. So there's with your first derivative, second derivative, third derivative. And that can be simplified because the 3 factorial, the 2 times 1 will cancel out the 2 times 1 in the 16. Now we have what's called Taylor's theorem with remainder. So if f has derivatives of all orders in an open interval I containing a, then for each positive integer n and for any x in I, we have our Taylor polynomial to the nth degree plus some remainder. And we typically just chop off this remainder, where the absolute value of this nth remainder is less than or equal to basically the n plus 1 term at a of the Taylor polynomial. And this is what we call Lagrange error bound. So basically, we are going to look at the worst case scenario. In order to do this, we need to know how far to take a Taylor polynomial so that we can stop. How many degrees is good enough? And the worst case scenario is when the n plus 1 derivative is at its maximum value. The hard part is determining what a value does this. This value depends on which endpoint creates a maximum n plus 1 derivative. So let's look at an example. Find the maximum error of the third degree Maclaurin polynomial of y equals sine x on the interval from 0 to 0.1. All right, so to do this, we first want to find the Taylor polynomial. In this case, the Taylor polynomial centered at x equals 0. So after doing that, I'm going to get that the third degree Maclaurin polynomial is x minus x cubed over 3 factorial. Now your next step is to find the n plus 1 term, which basically means that my remainder after the third degree has to be less than or equal to the sine of a over 4 factorial times the absolute value of x to the 4th. Step 3, determine at which endpoint n plus 1 derivative is a maximum value. So that means I'm going to take the 4th derivative at my first endpoint, which is 0, which means sine of 0, which is just 0. And I'm going to take the 4th derivative at 0.1, sine of 0.1 is approximately 0.0998. So what this means is that I can use the a value that gives me the biggest value of the 4th derivative, which is 0.01. So that means I'm going to rewrite my remainder less than or equal to sine of 0.01. Step 4, the value that you plug in for x will be the distance between the centered value and the endpoints. This function is centered around 0 because we have a Maclaurin polynomial. So that means that I have sine of 0.01 over 4 factorial times the absolute value of the value that I'm using for a, which is 0.1, minus my center point, which is 0, to the 4th power. Now I'm going to evaluate the error. So when I do this, I'm going to get a really small number, so I wrote it in scientific notation. This means that the third degree polynomial approximation of sine x varies from the original function by 4.1597 times 10 to the negative power. So when I look at this graphically, my red curve is my sine value, and my green curve is the Maclaurin, the third degree Maclaurin polynomial. And since I'm looking at 0, this error is super small. And as you can see graphically, it's pretty much the curves are on top of each other. So that means if I wanted to evaluate f of 0.03 of sine, that means sine of 0.03, and I didn't have a calculator, I would use this third degree Maclaurin polynomial, and if I was to plug this in my calculator, I would get this value. And if I was to evaluate this, I would get this value. And as you notice, they are pretty gosh dang similar. All right, now let's find the maximum error of the second degree Taylor polynomial of y equals square root x plus 2, centered at x equals 2, on the interval 1.9 to 2.1. So I first find my second degree polynomial, and I'm going to go ahead and set up my remainder, which has to be less than or equal to the n plus 1 term. And I need to figure out which endpoint gives me a maximum n plus 1 derivative, so the third derivative. So the third derivative of 1.9 is going to give me 0.0125. The third derivative of 2.1 is going to give me 0.01102. So that means that I am going to use the 1.9 derivative in my remainder. And now I'm going to go ahead and evaluate this remainder at the 1.9. So when x equals 1.9. And when I do that, I get the following. And that means that my remainder has to be less than or equal to 0.000002. Well, I hope you enjoyed learning about Taylor and Maclaurin polynomials, and I will see you in class tomorrow. Have a good night.